Friends, today we shall be discussing one of the very important topic of hydraulic engineering, that is open channel flow, and then in open channel flow we will be discussing the uniform flow. Well, now what is uniform flow? Some fundamentals of that we have already discussed in our earlier classes, and some of the topic that we have discussed in our previous classes that will also come in this discussion. And so let me recapitulate what we did in our earlier classes. Okay, we could see that open channel flow can be classified in different way. A different way means based on variation of flow parameters with respect to time, variation of flow parameters with respect to space, and then of course based on turbulence, then based on whether it is critical flow or not. So like that we can classify it in a different way, and this uniform flow is coming under the classification that we are making, classification based on variation of flow parameters with respect to space, and that way we did classify it as uniform flow and non-uniform flow. Now in this particular class we will be going more detail into the uniform flow. Well, then another topic that we did discuss in our earlier classes is that fluid motion obeys the basic physical principles of conservation of mass, then conservation of momentum and conservation of energy. Well, now these very basic principles we will always be using when we will be discussing this particular topic, that is uniform flow. Well, then in open channel hydraulics we found that which force is dominating the flow, that is the gravity flow. So when the fluid is in motion, which is the force that is causing the motion is the gravity flow, particularly when we are talking about open channel hydraulics. And then in a system when there is a force which is causing a motion, then some forces will be opposing that motion, and that opposing force is coming due to frictional resistance offered by the bed and the side of the channel. So that way these two forces depending on different obstruction, depending on the channel slope, and depending on the total volume of flow or volume of water that is coming, these driving force and the opposing force keep on changing, and that gets balanced at some point of time, and that way this makes the flow to sometimes become uniform flow, sometimes become non-uniform flow. And when I am saying that uniform flow, I am just considering that we understand what we mean by uniform flow in a simple term, and because that we have already discussed in our earlier class, that when that is the flow parameter do not change, when the flow parameters do not change with respect to space, that is, a depth is not changing with respect to space, velocity is not changing with respect to space, then we term this sort of flow as uniform flow. Well, now to go a little bit deep into this particular topic, we need to know that how a uniform flow gets developed. Well, so let me go to the development of uniform flow. Well, we can say that when the balance between the component of gravity force, and that again when we say component of gravity force, we are talking in the direction of flow, component of gravity force in the direction flow, and the resistance force, that is resistance force means the resistance offered by the frictional resistance of the bed and side. When these two forces get balanced, and when we achieve this balance within a channel reach, at any instant of time, then the flow will neither accelerate nor decelerate. We know that when the force are getting balanced, then there will not be any acceleration or deceleration of the flow, and that lead to the formation of uniform flow velocity. And when we are getting uniform flow velocity without any acceleration and deceleration within the channel reach, ultimately we are getting uniform depth at every point, and that flow we refer as uniform flow. Well, now one important fact is that for a given discharge, when a given amount of discharge is flowing through a given channel, means our channel section is fixed, suppose in that channel section a given amount of discharge is flowing, then this balance, that is the balance between the driving force, that is the gravity force, and the resistance force, can be achieved or is achieved for a particular depth of flow. This can be achieved for a particular depth of flow. Of course, there is an exception, that is the exception in case of circular channel. In case of circular channel, of course, there is an exception in that case, that will be coming later, but right now we can consider it like that. This balance is achieved for a particular depth, and that depth in fact we call as uniform flow depth, or there is another name for this uniform flow depth that we call as normal depth, because well, that normal depth means normally we get without any disturbance this sort of flow, so we call this as a normal depth. Now let me just give you one example, or let me explain this with some diagram. You can just concentrate on these slides. Say there is a channel of this slope, well, and we have put some amount of discharge Q here. Some amount of discharge Q is being allowed to flow through this channel, and say by some means we are putting this amount of discharge with a depth of this much. Suppose this is the depth. Well, this is the depth we are putting. That means the flow is in this part we are not showing right now, and this is the depth we are putting right now. Now, for this depth of flow, now what this amount of water will be having some weight in this direction, that is say weight W, and then this will be, if this has an angle theta, this is an angle theta, then this is theta, and then this will have a component of this force W in this direction, that we can write as W sin theta, and you just imagine that this channel is suppose like this, and then water is flowing like that, and we are putting some amount of water here like that. So this is like that, okay. And then from the side of the channel, suppose this is the channel boundary, top of the channel I am drawing here, okay. Now this force is trying to move the water in this direction. Then what force is opposing is that from the side of the channel and from the bed of the channel. So all this from the side of the channel, you just imagine side of the channel means I am talking about this one, bed of the channel means I am talking about this one. So that way from the side of the channel and from bed of the channel there will be opposing force. Now depending on roughness of this side or roughness of this bed, some amount of resistance force will be developed, and that will also depends on how much area, how much surface area is actually in action, that is how much surface area is in contact, and that way we will be getting a total amount of resistance force. Now if that resistance force is less than this W sin theta, that is force from this direction, then what will happen, that the flow will accelerate in this direction, that is velocity will be increasing, and then what will happen when the velocity is increasing, that flow depth as total amount of q is remaining same, and from the very continuity equation we know that simple continuity equation we are talking about, it is area into velocity. So, when our q is remaining same, flow is accelerating, velocity is accelerating, the flow depth will be reducing. So, when it is moving downward, then it will be coming like this, it will be coming like this. And then what is that? This again the gravity force, we are having this amount of water will be having a flow force in this direction, and again depending on the contact area of this particular flow with the side and the bed, resistance force will be developing. If it is again less, suppose this w sin theta is more, again the flow depth will be coming down and it is moving like this. So, that way after some time and some distance, what will happen? We will be arriving at a depth, we will be arriving at a depth, say this y depth, for which we are finding that the component of gravity force in this direction and the resistance force offered by the side and the bed are exactly balanced. And in that case, when the force will get balanced, this flow, there will not be no more any acceleration or deceleration, and then the flow is moving with the same depth in this direction, and then what we are getting is called uniform flow, and this particular depth of uniform flow we refer as normal depth. Okay. So, normal depth means the depth of uniform flow, that term we will be always using, that is called normal depth, normal depth, and normal depth means the depth of uniform flow. Okay. Now, here I am just saying about depth of uniform flow. Now, here I am talking about, suppose the flow is accelerating and from a higher depth it is coming down and we are having a uniform flow. The things can be just reversed also. For example, suppose we are putting some small amount of discharge, say this is again the bed, and we are putting a small, we are putting an amount of discharge q, but with a very small depth, we are forcing this depth. Say there can be some obstruction and we are allowing the water only to flow through this part. So, what is happening that this volume or the mass of fluid will be having some weight, and again this w sin theta component we will be having here, and then opposing force is suppose much more here, it is more, opposing force is increasing, then what will happen, that flow will be retarded, and then when the flow velocity is decreasing, then your depth is increasing. So, in the next moment the depth will be increasing like that, and that way the depth is increasing and it will ultimately reach a depth where again you will be finding that the force driving the flow and the force opposing the flow is equal. So, that way in a channel for developing a uniform flow we always need some initial portion. I mean in nature of course the things will be coming as it is and we can have different condition based on the different situation. Well, I will show that also, but in the laboratory if we try to develop a uniform flow, definitely suppose you are putting some water here, then initial some turbulence will be there, some ups and down will be there, and finally we are arriving at an open uniform flow. So, if we need to know in a laboratory channel what is the uniform flow depth for a given discharge, we need to just leave some portion in front so that we give sufficient space and time for uniform flow to develop, and then only we are getting uniform flow here. Of course, if there is another changes in the downstream, that uniform flow again can get disturbed. Well, and similarly if I talk about a natural situation, the same way we can have, and the flow can change from one say non-uniform flow to uniform flow, and then based on the slope change or based on some of the obstruction, natural obstruction, in the nature we can have uniform flow, we can have non-uniform flow. Well, say this sort of flow, let me consider, say a channel is like that and suddenly its slope is increasing like that, and then suppose again we have a flat slope like that, and then it is moving like this one. Well, I am not going into much detail of this thing. Suppose for a given discharge Q, we are having a uniform flow depth like this. It is from infinite extent, it is coming like this, say. So, it is coming with a uniform flow depth y n. Then when there is a change, then the flow will be coming like this in this point. That detail we will be discussing later, of course. Say the flow is coming like this, and here of course there will be critical flow, that aspect we will be discussing later. But again then the flow is coming down, and this part of flow is not uniform flow, because here as the slope is more, velocity is increasing v1, and here suppose here if I consider v1, here it is suppose v2, this v2 will be more than v1, that means there is acceleration and the flow is changing like that. And then after some time, based on the resistance of this part and based on the slope of this particular ridge, again it will be gradually moving to a uniform condition like that. And then here also we are getting a uniform flow y n, normal depth, and this is also normal depth. And then again suppose here we are going, there will be retardation, so flow will be rising like that, again we may get another, we will be getting another uniform flow here. Of course, if there is a drop like this, then there will be fall like that. Of course, based on how much is the depth here and how it is entering this particular channel reach, depending on all these fact, there can be different phenomenon, and I am just talking about a simple situation and drawing one typical case where it can be. Now, what we could see that for a given discharge, uniform flow or the normal depth in a channel we can have, here we are having this depth, here we are having this depth, both are normal depth, but here it is more, here it is less. So, what it means that normal depth depends on slope SB, bed slope SB. If your bed slope is more, your depth will be less, that is uniform flow will be moving with lesser depth. Bed slope is less means it is moving with a higher depth, like that. So, channel cross section will influence and bed slope will influence, and for the same bed slope and same channel cross section for a given Q, we can have single uniform flow depth, normal depth. Of course, with the change we can get another uniform flow depth. Well, so briefly saying about the development of uniform flow in nature, we can have like that. Then let me go to the another term or little mathematical expression of these uniform flow, and of course not some of the term we use, that is called say substantial derivatives. This is not directly related to uniform flow phenomenon only, but before explaining some of the term in uniform flow or in non-uniform flow even, or even in unsteady flow, we need to have some understanding of these term, that is the substantial derivative. Why it is important? Because we are talking about say acceleration, okay. So, when there is no acceleration, not when there is no deceleration, then we are getting uniform flow, right. But now acceleration of what? If it is a solid body, it is moving with a velocity v suppose, and then we can very well understand that this solid body is moving fine, and then it has a different velocity with time, what the change of velocity, time rate of change of velocity, then we can call this as a acceleration. But in case of fluid, there can be changes, because the changes are not that simple, and we need to have better understanding of some of these terms. And so, we refer, suppose when we say the change of velocity or acceleration we are talking about, that means time rate of change of velocity, then we need to talk it in this term. what we mean by substantial derivative. Of course, we use the term total derivative also. Well, but let me first explain these in physical term, and let me read this definition of substantial derivative first. Say instantaneous time rate of change of a flow parameter. So, it can be any flow parameter. Of course, when we talk about acceleration, then only we talk about velocity, but change of velocity, but this substantial derivatives, that term can be coming for any flow parameter. Say if we talk about density, suppose rho, density of the fluid, and if this density of the fluid is changing from point to point, time to time, then we can talk about the time rate of change of that particular parameter also. So, any parameter, any flow parameter we can talk about, and then we are talking about again instantaneous time rate of change, instantaneous time rate of change. Well, what we mean by instantaneous time rate of change? Instantaneous means at that instant of time, what sort of time rate of change of that flow parameter with respect to time we are getting. Again, at a different time, we can have a different rate of change of that parameter with respect to time. Well, so by substantial derivatives, we talk about instantaneous time rate of change of a flow parameters of fluid element as it moves through a section, as it moves through a section. Well, let me give another example to explain what we mean by substantial derivative. Well, say any parameter, let me not talk about even fluid, let me take a different situation where it may be very conveniently explained what is substantial derivative. Say let me, I am not good in drawing, but let me try. Suppose a person is moving in this point and he is trying to enter a building. Say he is trying to enter a building like this, and then, well, now let me talk about what are the changes this he can experience. Well, suppose there is a sunlight here, and let me talk about the sunlight is falling on this person, and then when he is entering through this door. So, let me talk about one parameter, say brightness. Let me talk about the parameter brightness. So, how the brightness of this person is changing. Okay. So, when he is moving from this point to that point, through this point he is entering. So, our interest is at this particular section we are observing, at this particular section we are observing where there is a door, and when he is just entering from here to here, then when he is inside, then say inside the house the brightness will be definitely less. Here we have more brightness, and here we have, inside the house we have less brightness. So, when the person is just moving from this point to that point, at that instant of time when we are observing, because of his movement from this point to that point, his brightness will change. Because of his movement from this point to that point, when he is crossing through this section, say my section is this one, through my section is this one, section I am talking about this section. So, at this particular section, when he is moving from this to that point, then his brightness is changing. So, there is a change in his brightness because of his movement, Well, so suppose brightness B, that is a function of space, suppose space mean I am writing as x, and also a function of time, So, when I am talking that he is just moving from here to here, at that instant actually time change is not coming right now. Say as he is moving from here to here, something is changing. But now again you imagine that when he is just moving from this point to that point, at that instant of time, some cloud has come, some cloud were here and that cloud has come here at that instant of time. Now, because the cloud is coming, for that also there is a change in his brightness. Because the cloud is coming, so brightness is changing, and at that instant of time, because of that, his brightness is changing. Now, that part of change is brightness has nothing to do with his movement from this point to that point. So, that means when he is entering into the room, at the same instant of time, a cloud cover is covering the sun. So, his total brightness from here to here is changing, and it has two distinct parts. One part is that at that instant something has happened with respect to time, and because of that his brightness is changing, and again as he is moving from this point to that point, so his brightness is changing. So, similarly, when we talk about a change of any parameter, suppose in the fluid field we talk about the change of velocity with respect to time, okay, it is the time rate of change. But again that has to do, here we need to think about that when a fluid is moving from one point to another point, and during that instant of movement, what is the change occurring due to each movement from one point to another point. Again, we need to observe that at that instant of time with respect to time what it is changing. So, that way we get two distinct components, and that two distinct component we just covering these two distinct component, we call this as a substantial derivative. Okay. We can write this in this form, that the notation used is say d dt. d dt is the notation, and this d dt, what we write, that this is the change with respect to, that is partial change with respect to this time, plus there will be another component, that is change due to the variation. Say if we are talking about a particular component, then I am writing in literal meaning here, I will be coming to the mathematical expression later. So, this is the change of that parameter with respect to time, and then change of that change due to its movement through that section. So, that way we can write. Well, now let me just see how we can express this substantial derivative. Well, let me just take one example. Say, let me take in Cartesian coordinate. Suppose we have a Cartesian coordinate, and in 3-dimensional space we are talking about, and then we are considering a small fluid element, very small, and then this is say position 1, and that is in time say t1, and it has a velocity say v. Now, when we write the velocity in Cartesian coordinate we are writing, that means this velocity will be having in space we are writing. So, this velocity will be having its component in all these different components. So, this component we are writing as, suppose this is the x direction, this is the y direction, and this is the z direction. And in vector notation, how we can express this velocity? This is basically we are because when we say velocity we give magnitude and direction, and so it is a vector quantity basically, and this vector this velocity vector we can, how we can express, say unit vector is I, then unit vector in this direction is j, and unit vector in this direction is say k. Then we can write that this velocity vector v is equal to say the value of this velocity in the x direction and y direction and z direction, we have some value. Suppose this is u, this is v and this is z. Then what we can write? That we can write that iu plus j into v plus k into w. So, that way this things will go, this expression is giving us the velocity at this point. Now, this and flow is moving from this to, suppose it is it is moving like this, and tangentially I am drawing this direction, and it is moving to another point here. Here it has, it may have another velocity v2, say it is suppose v1, this is v2, and this is the position 2, this is the position 2, this is position 1, and say this point it is reaching after a time t2, after a time t2. And now within this fluid element, this is a small fluid element, within this small fluid element which can be considered to be a single point only, and within this fluid element, let me talk about one property, say density, fluid density. Let me talk about, say, fluid density. Well, the fluid density, say rho, and let us first generalize, let us consider that the things are moving and everything can change there, everything can change there. Well, so this fluid density rho, it is basically depending on, it is depending on the time t, because at this time it can be something, at this time it can be something, and also it is depending on its position, it is depending on its position. So, position means here say its density is something, and when the fluid we are considering the density at this point, it may be something. So, this is depending on, say, x, that is the in Cartesian coordinate I am talking about, this is in x what is happening, then in y and then in z. So, this density is a function of these depending on all these different values, locate, position and time. Well, so we can call the density at this point, at the point 1. So, density, say density at point 1 is, say, rho 1, and density at point 2, and that when we are talking about point 2 means, well, when we are talking about point 2 means this is at time t1 and this is at time t2, this is at time t1 and that is at time t2. Well, so this is, say, rho 1 and rho 2. Now, from the Taylor series expansion, now if we just talk mathematically, the Taylor series expansion, a parameter is dependent on all these value, and then the Taylor series expansion, how we can write that rho 2, this is rho 2 is equal to rho 1 plus, we can write that the change of, say, del rho del x, partial derivative of this particular variable with respect to x at time at the point 1, that means I am writing 1 means at time, again time 1, okay, but the point 1 I am talking about the same thing, this into change in that direction, that is we can say that x2 minus x1, okay, say this is here, x2 minus x1 plus, we can write that change of this del rho del y again at the point 1, and what is the change in this particular direction, that is y2 minus y1, then plus, say, del rho del z, and what is the change in this direction, that is will be z2 minus z1. Again there is another part, that is del rho del t with respect to time, and then we are getting t2 minus t1. Well, and then again, of course, when we are talking about Taylor series expansion, there will be some higher order term, there will be some higher order term, higher order terms will be there. And of course, when these say small distances, and we are talking about very small distances, and we are expressing a difference, and this higher order term become negligible, and that way we can neglect this term, and then neglecting this term, what we can write. So, neglecting the higher order term, okay, higher order term, and dividing by, because our interest is to find how the things is varying with respect to time. So, and dividing by say T2 minus T1, dividing by T2 minus T1, then what we can get? Well, we can write this like that, that is rho 2 minus rho 1 divided by T2 minus T1, bringing the rho 1 in this side, and this is equal to, here we can write del rho del x, and we had say x2 minus x1, and this point is of course 1 divided by T2 minus T1 plus say del rho by del y into, this is of course in point 1, y2 minus y1 by T2 minus T1 plus say del rho by del z, this is 1 again z2 minus z1 divided by T2 minus T1, and then plus del rho by del t. Here again of course we can write T2 minus T1 divided by again T2 minus T1. So, this part is not becoming 1. Well, this we can have. Now, when we write this particular expression, this rho 2 minus rho 1 divided by T2 minus T1, and when we talk about say T2 minus T1 when it tends to 0, or say we can call say T1 approaches T2. That means we are talking about instantaneous time, when this time change is very insignificant. Insignificant means in a sense that very small, instantaneous. So, when T2 approaches T1, then for this condition, when T2 approaches T1, then say rho 2 minus rho 1 divided by T2 minus T1, this particular expression we write as total derivative substantial derivative d dt of rho, that is what basically we call as this one. And this now on the right hand side the same thing, if x2 minus x1 again here divided by say x2 minus x1 divided by T2 minus T1, if T2 approaches T1, that also can be expressed as del rho del x. Well, so on the right hand side we can write say del rho del x, and sorry, this this change in x with respect to time. This is what the we know that what we mean by velocity, that is the change of distance with respect to time. So, here also we are talking about change of distance, say x2 minus x1, this is the change in distance with respect to time, and we are talking about this change, that component of change, suppose there is a two-tail change, then in the x direction what is the change, and that particular change with respect to time we have already given the name that this is equal to u in our vector. We have said that this velocity, this is basically velocity in the direction of x. So, we can write it like that, plus say del rho del y into this will be v plus del rho del z into say w, that we were writing as w, and then plus say del rho del rho del t. Well, so this is what the substantial derivative, and when we write this term say for any variable, suppose now we were talking about the change of density and the variable we did consider as the density, but say we can talk about change of any variable, and that way the substantial derivative we can write that expression. Suppose del t is representing the change basically, and this we can write as say del t. I am writing the time part first, and then I am writing this part, that is this is a time part plus then this u del rho del x plus v del rho del y plus w del rho del z. Well, so this way we are writing the expression, and then again this can be expressed in vectorial notation also, as we know that one symbol is used normally in Cartesian coordinate as vector operator. So, in say Cartesian coordinate we use as a vector operator the symbol nabla is used normally to represent this particular vector operator. That is sometimes rather than making in bold, some used a dash here, and this is equal to say I del x plus j del y plus k del j. And we know that v already we wrote that v is equal to say I u plus j v plus I j k w. So, these two vector we can just combine here, and we can write an expression for this substantial derivative as say d dt, that is a substantial derivative, is equal to del t plus this velocity vector dot the nabla. Okay. So, these two component, distinct two component we are getting, this two distinct component, and this same expression we can also get from the very basics of calculus, and let me just explain that part. Say using chain rule of calculus also we can write if a particular variable v, again we are talking about, suppose here I will be talking about the velocity vector, because as we started we came to all these from the point that we need to know what is acceleration, and so when we talk about acceleration, basically we are talking about change of velocity with respect to time. So, we will be talking our parameter or flow parameter, which is important here, is the velocity we are talking about. So, let me talk about this velocity v, and we have already written this as this is a function of x, y, z and t, x, y, z and t. And so, by using chain rule of calculus, say change in the velocity v, we can write that as partial change of velocity with respect to time into that how much time has already elapsed. Suppose a small time we are talking about dt, then this is what is the physical meaning of that, the total change in the velocity is equal to partial change of the velocity with respect to time, and then this is giving you the rate, and then multiplied by actually how much time change has occurred, plus partial change of the velocity with respect to x and how much actual change in the x has occurred, then partial change in the velocity v with respect to y and how much change in the y. Similarly, we can write about z also, that del v del z into dz. Well, this is very well known rule. And then say acceleration dv dt. If we divide t, say dv dt, then what we can have, that will be del v del t plus del v del x into say dx dt plus del v del y into dy dt plus del v del z into dz dt. Now, what we mean by dx dt? Well, this is very common, that dx dt means the velocity, basically the change of velocity with respect to change of distance with respect to time, that is what the velocity dx dt. And this velocity we are talking that the velocity component in the direction of x, and we already wrote that this velocity vector v is nothing but that I into u plus j into v plus k into w, means it has three components u, v and w, and in a say Cartesian coordinate, in the direction unit vector I in the x direction, j in the y direction, k in the z direction. Well, so what we can write, this del x dx dt or dy dt dz dt, that can be written as u, v and w. Well, so we can write this is equal to dv dt is equal to del v del t plus, for this I am writing as u del v del x plus, for this I am writing as v then del v del y plus w del v del z. Well, so this acceleration term, we have two distinct components. One is, say I can bracket it from here to here, and then another term is this one. Now, all these terms, when we talk about the change of velocity with respect to time at any instant of time, then all these components will be existing subject to some initial understanding or subject to some condition. That means, what sort of condition basically we are talking about, that if the flow is steady. Now, again we need to call back what was steady flow, what was unsteady flow, that we did discuss earlier. Steady means when the flow parameters are not changing with time, that we call as steady, and when the flow parameters are changing with time, then it is unsteady. Now, when the flow parameters are not changing with time, suppose it is a steady case, then what will be the rate of change of any flow parameter with respect to time? It will be 0, because it is not changing at all. So, del v del t term will become 0 in that case. But if it is unsteady case, when there exists a change of flow parameter with respect to time, then only this term, that is the first term del v del t will be there. And then when there is a change of parameter with respect to distance, then let me come to uniform and non-uniform. This part, that is the second part. Second part is basically representing the change of that flow parameter with respect to space. X, y, z means we are talking about change of this parameter with respect to space. And when some flow parameter changes with respect to space, then that type of flow, if we remember or if we recall our earlier discussion, then that type of flow we call as non-uniform flow. If the flow parameter, whether it is velocity or depth, when the flow parameter do not change with respect to space, then we call that as a uniform flow. Well, now that means all these component or all this value of the second term will be existing in case of non-uniform flow. Now, we need to know that or say we need to appreciate this point, that why discussing the uniform flow we have started with all this deduction and we have come to a situation that in case of uniform flow this second term will also not be there, because there is no change of flow parameter with respect to space, and if it is a steady case there is no change of flow parameter with respect to time. But we need to understand what we mean by that, that is it is not there means how it is not there, that we need to know. Again say we did discuss in the classification of flow, we did discuss about one dimensional, two dimensional and three dimensional flow. And here as we are writing this velocity vector as say in the component of u, v and w, u, v and w, that means we are considering three distinct direction, it has component in three distinct direction. So, we are writing this like that, and that means we are writing this for three dimensional condition. But for many flow situation in nature we consider this as one dimensional, and then when we make one dimensional some of these component will not be there. Now, say let me write this expression dv dt, and say our case is one dimensional, okay, one dimensional. That means velocity only we are talking that, suppose x is the only direction and the velocity we are talking that velocity in the x direction is equal to say v. Well, so now what we can write, that dv dt is nothing but equal to del v del t plus v del v del x, v del v del x. This is in one dimensional case. Okay. And this particular component, that is in when we talk about two-tail acceleration, then we have basically two components, this component and that component, and this component we call as local acceleration, and this component we call as convective acceleration, local acceleration and convective acceleration. Well, out of these two distinct component, local acceleration and convective acceleration, for say uniform flow case dv dt, if it is unsteady then only this del v del t component will be there, and this v del v del x, this convective acceleration part will be 0. Convective acceleration part will be 0 for uniform flow. The reason is that in fact when we are talking about uniform flow there is no change in the direction, there is no change in the velocity with respect to x. So, this component will become 0 for uniform flow. And then if we say that it is a steady uniform flow, then what will happen, that this del v del t component, as we have already discussed, this will also become 0. So, what we are getting, the total acceleration dv dt is equal to 0. Well, then when dv dt equal to 0, we are meaning this as steady uniform flow. Of course, if we mean that only del v del x equal to 0, when we say that only del v del x equal to 0, that also means that it is uniform flow, but it may not be steady. But when we talk about steady uniform flow, then del v dv dt equal to 0. Well, but in our earlier discussion also we did mention that in reality it is very difficult to get a unsteady uniform flow, because say at any moment of time, suppose our flow is here t equal to t1, then next moment of time if t equal to t2, we are having again a uniform flow. So, uniform flow means everywhere it is same and everywhere it is same, like that. So, this sort of changes is not possible. So, that way, say when we say dV dt is equal to 0, it means that V is equal to constant, V is equal to constant. And then when we say total V is constant, total variation of velocity with respect to time is constant, means we are also meaning that del V del x is also equal to 0. And V is equal to constant means if a same discharge is coming, here also V, here also V, then our depth is also constant. Say this is y, this is also equal to y, and that is what we call as uniform flow, where our velocity is constant all through and it is not changing, and when our depth is also not changing. Well, so y, and this depth of uniform flow is called normal depth. Okay. Now, with this discussion on uniform flow, we could understand that by uniform flow what we really mean, and then now as we did discuss that it is basically we need to balance the component of gravity force and the opposing force, that resistance force offered. Now, resistance force offered, to calculate it analytically it is very difficult. So, many a time we use empirical relation for expressing the uniform flow condition. These are the fundamental understanding, but we need to take recourse to the observation, we need to take some of the value empirically, and that we will be discussing in our next class, that how we express this relation of uniform flow balancing the component of gravity force and the resistance force. So, thank you very much.